Which one is north and which is south? So it's south, north. This one is south. So here's how you think remember, right? Here's how you think remember. The one that's going clockwise, shaped like a S. You see that? So this is your south. And then the north shaped like this. Right? The north going in a counterclockwise direction. So this is a north pole. Okay? This is where we stopped last week. So the first rule that you learned was the right hand grip rule, right? So it's right hand grip rule. All right, copy it down. Well, add that in, and then let's move on now to a flat foil. Flat foil. For the student class, right? You cannot leave that door open, right? It's very hot. Somebody got their company and take about 2 down again. All right, so let's remember that now, please. The channel will keep them closed. Okay, so after you write that, we're moving on now. This is just a straight wire. One piece of wire carrying current in or out. Now, I am going to take that wire. Pretend this is a piece of paper. I'm going to take the wire and I'm going to run the wire through here, forming a little coil. Right? So I'm going to do this. I'm going to take the paper and I'm going to connect it to a circuit. And I'm going to push the wire through the paper and then come back on in like that. You see that? So I'm taking the wire from the circuit and I'm pushing it through a piece of paper and then allowing it to come back through again. So now what I have drawn here is what we call a flat circular coil. Right? So this is a flat circular coil. First thing we have to figure out is what direction the current moving in. What direction is current moving? That's a load, right? To make sure the circuit not short circuit. Yeah. What direction is current moving? From positive to negative, right? The long terminal is positive and the short terminal is negative. So current going this way. Up here, down here. You okay with that? So the current's coming out of the paper here or into the paper here? Out, and current going in here, right? So what I want you to do for me is to draw this diagram and using what we learned a little while ago, draw what you think the magnetic fields like will look like here and what it will look like here. Well, what did we say current doing here? Current coming out of the paper here, right? So look at what we just learned. And current going into the paper here. So look at what you just learned and see if you could draw the P lines here. All right. So head up, flat circular coil. Right. Remember, it's on the magnetic fields, right? So we draw the magnetic fields around straight conductors. Now we drawing the magnetic field around a circular coil. So draw this diagram, head up flat circular coil, and draw what you think the magnetic field will look like here and here. All right, try it on those two places. Ready? So, what you all think? Very diagram a little small. But how is current behaving here again? Current coming out. So what it look like this? Current coming out, right? Current coming out, so therefore it will move in a anti-clockwise direction. That's okay? And here will be a what pole? Here will be a north pole. Well, what about here? It will move in a clockwise direction and we have a south pole. So if I ask you to draw the P lines along a straight conductor, you draw this. If I ask you to draw the P lines along a flat circular coil, draw this. Right? Now I'm going to ask you to draw it for something called a solenoid. So more than one flat coil. All right? That one a little bit harder, so we'll take the time and do that, right? Have to use it? No, because we have the actual wires here. You okay with that? So the first thing we learned today, we learned to draw the magnetic field lines around any kind of conductor. All right. After that, we're going to go back into something I was talking about last week. So our second diagram will be a solenoid. All right. So a solenoid. So what you see? I'm going to draw two versions of it. The second one is the one I want to really focus on, right? But the first one will help us figure out where the second one came from. All right, so what you see? We have, right, and we have our little load there. So we have current going from a plus to a minus, right? Positive to negative. Are you okay with that? Watch how the current behaving, right? So when it's here, it's going in at the top, coming out at the bottom. In, you're seeing that? And it's forming something called a solenoid. Right? A solenoid is like a big spring with current flowing through it. You're seeing that? So as the current flowing, it going into the top, it going in at the top, flowing here, and then coming out at the bottom. You're seeing that? In at the top, out at the bottom. In at the top, out here. Right? So it's behaving like that. And then it's coming here and then coming back out here. You're seeing that? So you have to follow how the loops being formed, right? They're going in and out. But so you recognize that everything on top is in and everything at the bottom is out. What's the symbol in again? And what's the symbol for out? That's okay? So I just joined 3, right? So this is a solenoid, this is a solenoid. These are the symbols for it. You all see where this came from? Yeah? Next to Elena. You okay? What's the name again? Josh? Right? Josh, you follow this? Right? This is the symbol for current going in. This is the symbol for current coming out. So instead of drawing this city, give me 5 minutes again. It'll last long. Right? Just give me 5 minutes. Start it now, right? Current going in, current coming out. Okay with that? Right. How do we figure out what the magnetic field lines look like? Well, what we have to do is go back to the right-hand rule and use the right-hand rule in reverse. So whatever the fingers were, thumb now is. Whatever the thumb was, fingers now. So it's a little bit different, right? So we're using Fleming's right-hand rule. So this is technically our second rule. The first rule, current direction, magnetic field. Second rule, using the same right-hand grip rule as this. Your fingers point in the direction of current and your thumb point the direction of the magnetic, to be specific, not field, magnetic north. It tells you where the north is. And if you know where north is, you know where south will be. So let's try it here. Fingers, current direction, thumb, direction of the north. That okay? Upside down. Watch here, right? Make sure you can use it. Current going what here? In and coming out. Look at my hand. My fingers going in at the top and coming out and bottom. You see that? So I'm going in and I'm allowing it to curl so it comes out. Right? So it's coming out here and going in at the top. Must use your right hand and your thumb will point towards magnetic north. And if here is north, then here is, and magnetic field lines always what? Magnetic field lines always leave the north and come into the south. That's okay? Magnetic field lines leave the north, come to the south. Leave the north, come to the south. That's the way you draw the field lines. Okay? Are you okay with that? So I just want to give you a few steps to remember. What was the first thing I did? First thing I did was I found the current direction from the solenoid. Second thing I did, after I figured out the current direction, I used the I used the right hand grip rule to find the North Pole. And the third thing I did was what? What's the third thing I did? I drew the draw the field lines. Right? Okay? Draw the field lines. Always remember that they leave north, and they go towards south. All right? The reason I was giving these steps in point form is that these things easier to remember than me calling out a long essay. Right? So when you revise it, try to create your own little steps. Okay? And learn your steps so you can put it together. All right? Because the diagram won't always look like this. I could change current direction and you have to change everything here. So once you understand these steps, you can do it fairly. Are you okay with that? Right? So again, we're using the right hand rule, but we're using it in reverse. Fingers, current, thumb, north. Are you okay with that? Copy down this and copy down the new version, right? So call this rule number 2. All right? Call this rule number 2. Online, you're okay there? Hello, great. Got him? You okay? That's down here. Tanya, are you there? Yeah. Good. I think that's why. Photograph. Good. Good. Sit up there. Up and on. Yeah, four weeks. Then they go. There we are. Straight up. There we are. Đi lại chưa? Học rồi vậy. Đi này. Cái nào? Tự nhiên. Tự nhiên. Allora, ci dove ne sono le cose per Francis, so you didn't message Francis with the classes? Classic covered it, wasn't it? Classic. David. You get it back? I simply found it. Oh, I'm mixing up Dan and David. Sorry, David. That's not? That's wonderful. Wait, looks like David on that one. Ready? Are you okay with us? We are not taking it. Oh, let me check the contract. Write on everything, huh? Write on 3 steps as well. All right, let's go again. So we learned about the rule number 2. We learned 2 rules, right? Current along a straight conductor, current along a solenoid. Now, what has happened when you bring 2 magnets together again? They either attract or repel, right? So whenever you bring 2 magnetic fields, either you experience a force of repulsion or a force of attraction. All right. But here's what I'm going to do now. I am going to take a conductor and I'm going to put the conductor inside a magnetic field. All right. And let's see what will happen, right? That's going to bring us to our third rule, right? Fleming's left-hand rule, right? And it's real simple. Thumb, 90 degrees here, thumbs, 90 degrees here in between. Right? So it looks like that. All right. So next subheading, current carrying conductor in a magnetic field. Current carrying conductor in a magnetic field. Current carrying conductor in a magnetic field. You all see this here? Here we have a current carrying conductor, right? Current comes in or out, right? So there is a magnetic field associated with this conductor, and there's a magnetic field between these 2 magnets. That's okay? When those 2 magnetic fields interact, this conductor is going to experience a force. And the force will either push it up, push it down. All right. I want to, before I give you a note, I want to show you how to figure it out. Right? So you're using the left hand, right? So you're using Fleming's left hand rule. right? And then your fingers like this, thumb, first finger, middle finger, right? So your thumb represents the direction of the force, right? Your first finger represents the direction of the magnetic field. And your middle finger represents the direction of the current. Huh? Yeah, pretty diagram. That's okay? So force, or some people call it thrust, because T is a thrust. Magnetic field, first finger. So they remember F for field. And second finger, the C in second, is current. Right? Yeah, there's second, middle finger, second finger. 1, 2. 1, 2, 3, 4, 5. Yeah. Yeah, 1, 2, 3. Check and roll. 1, 2, 3. Right? Anyway, it don't matter, right? Thumb is the direction of the force. That's what we're trying to find. First finger, direction of the magnetic field. Middle finger, direction of current. That's okay? So I want to show you how to figure out the force, right? Real simple. Do not, right? I know some people fingers are a little kind of weightish, and it'll be like this, right? But try first to keep your fingers 90 degrees from each other, right? And whenever you're moving, you can move around, you can move your wrist. Don't move your fingers. All right? So you can move your wrists around, you can switch your positions, but you're not moving your fingers, right? You don't want to end up with this. Right? You want to keep it like this. All right? Yeah. Ready? So let's see how it works, right? Let's see how it works. Say it. Huh? No, it's the same. All right. So watch this here. First thing we start with, magnetic field. Magnetic field moves from where to where? From north to south. So your magnetic field moving in. Magnetic field moving in this direction, right? I don't want to draw it yet. I will show you why it happened, right? But magnetic field north to south. You'll see that? So first finger going this way, left to right. But that's a personal term, right? For the same. What does the dot and the circle mean again? Out. So it means current coming out. So your middle finger points outwards. That's okay? So your middle finger pointing out, your first finger pointing left to right, and your thumb will automatically point in the direction of the force. So in our example, the answer is upwards. Are you okay with that? But why that happened? There must be a reason why it happened, right? You all remember when a north and a north repel, it's because the magnetic field is not interacting, and a north and a south, when they are attracted, because the field is interacting, right? Here, the reason it's getting pushed upwards is because the field lines between the north and the south normally look like this, right? But the problem now is that the field lines, they kind of bulk up underneath. So your field lines, most of your field lines come in here. So if most of them here and just like one on top here, what will happen? If most of your field lines underneath here, it will push it upwards. That's okay? So the field lines bulking up underneath here and pushing the conductor. You okay with that? You okay with that? So that's the way we use Fleming's left-hand rule. All right? So draw this, write this, and I'm going to give you a note. Then we'll do about 6 examples, and I'll pick 6 people. This here, this is really the principle behind a motor. Right? What is happening in a motor? You plug it in, and what is happening? Something is caused, something is to move, right? Yeah. So this is basically what happening. When you plug in the current, there's a conductor next to a magnetic field causing it to move. So your homework, want to plug motor and dig it up and see how it goes. Right? Find out something. Right up here. Experience current and experience. There'll be another. Yeah, the guys that there, the box. Ready for note? A small note, a small note. Ready? By the small note, when the current carrying conductor is placed within the magnetic field, one second, what was that? When the okay, when E slash the right, so let me put that. Right, when E slash the current carrying conductor, current carrying conductor is placed between a magnetic field, is placed within a magnetic field, between a magnetic field, their magnetic fields interact. Their magnetic fields interact. Their magnetic fields interact. Causing a force, causing a force, causing a force to be exerted. Well, if I get cooler, no? Okay, however, cooler, no? Causing a force to be experienced on the conductor, exerted on the conductor. Exerted on the conductor. And I'm sure you'll have different words that you can use. Exerted on the conductor. Full stop. The direction. So can you repeat now? That's not. I started magnetism. When the current carrying conductor, you know, Richard? Oh, when the current carrying conductor is placed between a magnetic field, comma, you wrong to do that. Their magnetic fields interact, causing a force to be exerted on the conductor. Causing a force to be exerted on the conductor. Full stop. The direction of this force, the direction of this force is given by Fleming's left-hand rule. right? So, right? And I give you an example here. You have the example. All right, so I'm gonna give you four more, right? Four more, and I want you to work it out for me, right? All you figuring out is the direction of the force, right? If we can draw the P lines, do that as well. North. Now let me change them to south. Let me change them to north and put a X in the middle. Let me change them up here. In case you see the little pattern and change them up here. Yeah, and let me change them for south here. And put back a dot here, so see our pattern. And then let me confuse up the whole thing here. Let me confuse up the whole thing here. And put a note here, X here, and a something. This one will have. Go ahead. Use the left hand rule and figure out all for the direction and the force in each one. Go ahead, have fun. You know, have it one, do it, right? Okay, you have one on the board, there's two on the board. Anyone? I'll help you. Pick anyone. You have a black, blue, and a blue. No. If you let purple,
Get the questions there. You want to let's talk into mine. This is so I
want to try the first one? Sorry, ma'am. Come. Right, and you're doing the first one here. Right, so before you start the question, get your fingers in order. Right, so come. Make sure you remember which is which, right? Thumb is, first finger is, and middle finger is. No, don't move it. All right, right. Start with magnetic field direction. Magnetic fields move out, right? So let this finger point so. Yeah, come this, right? So don't move your finger, right? Notice out. X means what? X means in. So therefore, your middle finger should be pointed inwards. And the answer is thumb. Thumb pointing where? Up. Right? Watch again, right? Magnetic field. So I started with the magnetic field moving north to south. Right? Magnetic field moving north to south. Current going what? In, right? So my middle finger going inwards. So my thumb pointing upwards. Done. Right? And then you can draw the little field lines here. Draw them here. Draw them here. Draw them here. And draw them here. And I got something wrong. What I got wrong there? Arrow. You say I know that. Who's that? Great. All right. Come, David. Come and do number 2 for my David. Okay, number 2. Capitán Tony Fred. We saw the big party más de día. Aquí. Right, line up first, right? Line up. Magnetic field going where? So. Magnetic field is moved from north to south. So this finger to point where? Wrong, right? Watch. North to south. Current going where? Dot. Dot is what? Dot is out. Right? So your finger, the middle finger, point where? Right? So the current, magnetic field, current coming out, and the forces. Very good. That's all right. Go. You could be forced to them. No, but you show how you get the others. Yeah, looking like you show. Watch again. Magnetic fields move north to south, so I'm lining up this. Yeah. And dot means current coming out. So once these two line up, you'll figure out the answer here. Right. Give somebody this one from now. Anybody else? Anybody else? All right, come. Number 3. Who got it there? I didn't get exactly. Who what? Come on, Shine. I'll help you. Come, I'll help you. I said, team already. You give it the name again. Come. Come on, I'll help you. What's the name again? Egypt. No. Yeah. Name again? Huh? Salawi, you help us out here. So first thing first, line up, make sure you remember. Right? Make sure it's straight, right? So magnetic field is somewhere away. North to south. So let this finger line up north to south. Right? This means what? In or out? It's out, right? So it's somewhat a middle finger at the point. Out. So the force is ready. Very good. Give it who understands? Come on, do the next one. Someone try the last one for me. You'll do it here. Anybody confused? We're all confused. Very confused. All right, sit down. Very confused. Yeah. Come on, help you. Right? So what you have to remember, right? All you have to do is figure out what direction magnetic field is. Magnetic field is north to south. Okay? And when you figure that out, figure out the current direction. Once you figure out these two, this will automatically be the answer. Right? So line it up first. Left hand over. Right? So you have your force, trying to find that magnetic field, current direction. Magnetic field always move where? Right? So line it up north to south. Right? X means what? In or out? In. So you have to make this middle finger point inwards. Yeah. Yeah. So you had a root in the hand. So now current direction, magnetic field direction. So the forces down. That's all. So you are the kind of do the rotation. If you don't want to move your hand, move your notebook around. All right? Anyone you want. That's it. Right? Watch it again. Magnetic field, north to south. X means in, so my thumb automatically pointed downward. Are you okay with that? So that's the way you use Fleming's-Lackan rule. Right? Why are we using Fleming's-Lackan rule? I want to show you one more thing. Last thing on there. I just want to show you how it works here, right? I just want to show you one more thing and then that's it, right? What is simulation here? Right? Why is we learning all of this? Well, the reason we're learning all of this is to be able to understand the way the motor works. Right? So what is simulation here? Right, which one? Where is simulation? Java lab would normally be nice. Right, online, you'll see enough. Online seen it. All right, nice. Okay, so what is here? That is a simple DC motor. We have to explain Josh how that works, right? What shape is, right? Very simple. That black thing, we don't think that is there. Okay, this dark colored thing. What is that? What is that earlier? This here. Right, that's the wire carrying the what? Current. This red and this blue is the what? Right. So what will happen to that coil? It will experience a force. Right? To be a little bit more exact, what you see here. Here's the plus. Here's the plus, and here's the minus. So current going plus, so it going here, and it going down here. You're seeing that? Current going this way. Y'all okay with that? Everybody okay with that? Yeah? So the current going from plus to minus. Now, let us pretend, I don't know which one is the north, which one is the south. That's not right. Right, the north is the red. Right, the north is the red. So let's use the rule. If the north is the red, can you figure out what force this will experience here? Let me almost last. Watch this here. Here is the north pole and here is the south pole. Right? Watch it there. Current direction to the magnetic field going from red to blue. You're seeing that? and currents going up. So I'm going to take my finger and point it upwards. You're seeing that? Watch it again. Magnetic field, red to blue, current going into the TV. Right? So the force is where? Downwards. So the force is downwards. And if you work out the next side, it's forces. So how will that turn? If I give you a coil and one experience down and one experience up, it will turn like this. All right? And what the motor allows it to continuously turn in the same direction. Right? That's the principle behind the motor. Let's run it and let's see if that's correct. Yeah? Yeah? So what you have to do is you have to explain how the motor turns like that. Yeah, well, that's what we do next week. We have full explanation. Okay? Everybody okay with that? You'll see how what we did build up into this. Don't forget next week. Yeah? You know what? I can sit down here and everything no one all gonna come up here and explain it. I'll make you do a video. Okay, what you can do? Do a video and send me the video. And I'll do. All right, nice. That's it there, right?